Hello everyone, in today's video we'll be discussing on addressing modes. Here's the content for today's video. Firstly, we'll be discussing on the introduction to addressing mode, types of addressing modes, immediate addressing modes, indirect addressing mode, direct addressing mode, index addressing mode, relative addressing mode, auto increment addressing mode, and finally the conclusion. Introduction. Addressing modes are essential techniques employed by processors to locate operands within memory, thereby determining how instructions access the required data. The efficiency, flexibility, and complexity of a processor's instruction set are directly influenced by the addressing modes it utilizes. By defining how instructions interact with memory, addressing modes play a pivotal role in shaping the overall performance and functionality of a processor. Different addressing modes offer varying levels of efficiency and adaptability, impacting the overall execution speed and versatility of a processor's operations. Understanding addressing modes is crucial for designing and optimizing processor architectures to meet specific performance requirements and application demands. These are the types of addressing modes that we'll be discussing in today's video. Firstly, we'll discuss about immediate, followed by direct, indirect, index, relative, and auto increment addressing modes. Immediate addressing mode. Immediate addressing mode involves specifying the operand directly within the instruction. With immediate addressing mode, the CPU can immediately access the value of the operand. In the instruction move R1, to #5, the operand value of 5 is directly specified for immediate processing. Immediate addressing mode facilitates efficient utilization of data by embedding it directly into the instruction. This addressing mode is particularly useful for operations where the operand value is known at the time of coding and does not need to be fetched from memory. Direct addressing modes. In direct addressing mode, the operand represents the memory address of the data. The CPU accesses the specified memory address to retrieve the operand. For instance, in the instruction move R2 to 2000, the CPU fetches the value stored at memory address 2000. Subsequently, the retrieved value is stored in register R2. This addressing mode directly accesses the data from memory for processing. Indirect addressing mode. Indirect addressing modes involve accessing a memory address stored within a register or specified location. The CPU retrieves the memory address specified by the operand and then accesses the data stored at that address. In the instruction move R3, R1, the CPU fetches the data from the memory address stored in register R1 and transfers it to register R3. This addressing mode enables flexibility in accessing data stored in memory indirectly through pointers or addresses stored in registers. It requires an additional memory access step compared to direct addressing, where the operand's value is directly retrieved from a specified memory address. Index addressing mode. Index addressing mode involves calculating an operand's memory address by adding a constant or register value to a base address. The resulting memory address is determined by the sum of the base address and the offset. For instance, in the instruction move R4, R5 plus 10, the CPU computes the memory address by adding 10 to the value stored in register R5. Subsequently, the CPU accesses the value stored at the calculated memory address for execution. Relative addressing mode. Relative addressing mode utilizes the current program counter or instruction pointer to determine operand addresses. The effective address is computed by adding the offset or displacement value to the current program counter. For instance, with the program counter at memory location 1000 and an offset of 50, the effective address becomes 1050. Auto increment addressing mode. Auto increment addressing mode automates the incrementing of operand addresses following each access. This mode finds frequent application with arrays and sequential memory access scenarios. Upon access, the address automatically increases by the size of the accessed operand. It simplifies the process of iterating through arrays or accessing consecutive memory locations. Auto increment addressing mode streamlines memory management tasks by handling address increments automatically. The assembly language instruction LDX $1000, Y plus utilizes a base address and an index register to compute the effective address. The effective address for this instruction is determined by adding the content of the base address denoted by $1000, with the content of the index register Y. In the context of this instruction, the value stored at the memory location $1000 is considered the base address. By utilizing the index register Y with the Y plus syntax, the assembler automatically increments the index register after the effective address calculation. The effective address calculated by this instruction represents the memory location from which data will be loaded into the X register or accumulator, depending on the specific architecture and instruction set. Conclusion. Addressing modes facilitate efficient and flexible access to operands in memory for processors. The selection of addressing mode significantly impacts both the complexity and performance of the instruction set. Each addressing mode possesses unique strengths and weaknesses, influencing the architecture's overall efficiency. The decision on which addressing mode to employ is contingent upon the specific needs and constraints of the processor's instruction set and architecture. Thank you.